continue. So yesterday we did or we learned some simple syntax from GGPLOT2 package, and today is just a matter of continuation. We touch on the normal basic syntax. From there we do another package for data visualization that is called the Lattice package. The other package is called the Lattice package. If you are very keen yesterday, you will note that to build a GGPLOT, we will just apply the simple syntax like this one here. So we will use the following basic templates that can be used for different types of plots, and from that point we will be good to go. And let's see how we can implement that language. You remember very well, when you are visualizing, this is the syntax that we will be using. So anything that we add must be captured inside this syntax. So it must be captured inside this syntax. The syntax on line 8. For GGPLOT, how do we do? We apply GGPLOT. We define the data first. The AEC, the aesthetics, is just the path for mapping. What we want to be included in our mapping. Then the geom function, this part here. Geom is a common name used here, but now at the function, when you want to do a function that or when you want to perform an operation that captures or that emphasizes more on a certain object, let's say the point, you want to join point, that's why at the function here you will have to insert the point function. Or if you want to have a GGPLOT of histogram, for example, you include geom underscore bars or geom underscore pie charts, like that. Then what we define inside here is the what do we call this? The characteristics of the of the graphings. So for example, you want to insert the legends. Legends in this package or in art programming is used to insert, for example, things like titles, the keys. For example, you want to say that black color represent this. You understand what I mean by a key. So you insert everything here. So that is how we do it. For example, I want us to do an operation of GGPLOT, or rather a graphic, using the inbuilt dataset called plant growth. We have inbuilt dataset called plant growth. If you run this command, you will get data of plant growth. So when you execute the plant growth, you will get these things here. So you will get, we have the weight of the plant, then we have the group here. We have group 1, for example. Here we have 3, 1, we have 2. Yeah, those are the, that is what is under group variable from this data set of plant growth. If you learn, if you do more research, you will just know the origin of this data set. It's there online. But now what I want is just to do visuals using this particular data. Now I want us to check on what I've done here. The command on line 12, then you compare it with command on line 8, the syntax for that particular command. So we have the GGPLOT. Remember, this BP here is just the name of a vector that I have assigned everything that takes place here. So that I can call this output anytime using any figure. Yes, if you check Kinde here, we have GGPLOT, then we have data is equals to data. This is where we insert our data source. So we are using what? We are using the plant growth. That's why we have the plant growth here. Then from there we have to do mapping. What we need to include in our graphics or in our visuals. So that is the aesthetic part. We have, now check here, we don't have to write this part here, mapping is equals to, or data is equals to. No, we have to write only this part. So only this part. So this is the data. From there I write this part from the aesthetic up to this point. So under mapping, I want my group. Check here, group is this part here to take x-axis, and my weight to take y-axis, and my weight to take y axis. What operation do I need to do under this activity or this task that I want to perform here? I want to do an operation on specific point. Remember, this point is for example, you want to take the value of x and the value of y. So this is, let's assume we take the first three. We will have under x-axis we have control 1, and on y we have 4.17. so that is my first point. So operations that are done on point is what we want to do. So ggplot, okay, the operation cannot be completed because I have not called the library. So check the error here. Error in ggplot could not find the function ggplot, so it means I have not executed the library in ggplot2. I have to call it. So you insert your cursor there, then you call it. Then from there you can call the second one. Okay, but I'm sure we will not be using the second plugin. So you can run this command here. Yes, it has executed. Then you can call that everything that you have done here. Remember, I have assigned it, for example, in BP. Then I can call BP to see the output that will be taking place here. So I call the MVP, I run the command, and you see what we have here are points. What we have in these graphics or in these plots are just points. So we will check. I want you to be very keen here on geom point. We will be changing this part here to display anything that we want. So you can we can have geom histogram, you can have geom anything. So I think that way we will understand more. Do you have any question up to that point before we continue? Do you have any question? Anything to say? Okay, nani ameelewa? And the ggplot, how we specify what we want to produce. You can produce an operation that is taking place specifically on point, for example, on histogram, for example, on bar charts, on a line graph, for example, and many others. Yes, so acha tuendelee mpaka pali we will finish what we were supposed to cover up to yesterday. So this is just a recap. We haven't introduced what we are supposed to cover today. So another thing, or another example, we can do an example on Iris dataset. I'm sure you are familiar with this dataset. When you call this dataset, what do you get? The data of flowers, and data concerning flowers. So we have it here. Yes, we have the sepal length, sepal window, all these things. I have assigned this operation to a vector count p, for example. So what do I want to do? I want to do a ggplot. I want to plot something on Iris dataset. Aesthetics, I want to do my operations on sepal length, sepal wind. Then I want to color species. Remember, color before we continue, on this part of aesthetics, you can include other words, other functions in R. So for example, color is equals to species. It means your species will take specific colors. It will be assigned by default specific colors. If you have two species, you will have two of them being assigned each different colors also. So this part will produce colors from different species. Remember, we have a species here. We under how many species? We end 3: Setosa, Vanginica, and which is the other one? Let me see. Vascala. Yeah, the other one is Vascala. Then plus jump point. So I want everything to take place, or to plot point on sepal length and petal length. Sepal length and petal length. So it means, for example, let's take the first leaf here. Let's take the first leaf. My display here will be like this. I want to display points geom underscore point. So I want to display point on the first one. Sepal length is 5.1, and the other one is 1.4. The other one is 1.4. So this is x and y axis. Then you can display the output. Let's see. And remember here, inside here, when you assign two values, two entries, for example here, the first entry will be assigned to x axis, the other one on y axis. So by default, even before you specify. But check here, you can reassign these ones here. You can reassign axis. For example, you take sepal length to this part and the petal length to this part. So for example here, sepal length is on x axis. You can specify it to be on y, for example, y, and this one to be on x, for example. Let's see. So I want to interchange these ones here, sepal and petal. So let's see. Yes, you can see we have the sepal here, we have petal here. But if you remove, or if you don't specify the axis, the compiler will assign the first one to x and the second one to y axis. The second one to y axis. We have another one here for the empty cast. You remember that package or the dataset for empty cast. So if you have any question, you can ask. So you can ask. Let's see. You can see that what we have. Yes, Mr. Kabila. Yes.
But the difference between, like, for now we have the color inside the aesthetic.
Pardon?
Like for today, coloring is done inside the aesthetic attribute of this GGPLOT. But yesterday it was inside this. Hello?
Buongea sasa, unaongea ukikatakata sauti.
Nilikuwa nasema for today we have the color inside the aesthetic attribute of the GGPLOT too.
Yes.
But yesterday it was inside this geom point. So what's the difference?
It can be anywhere. It can be anywhere. That's why I told you that if you are specifying a color is a function in R. So color, you are not counting color actually. Color is a function. So and remember, a function can be anywhere. Can be anywhere within your code. For example, you can have your color even outside here, even after the reason data set here. So this is just a function in R. This is just a function in R. So it can be here, ama ikuku kwa point. So anywhere it can fit, but you have to be keen. Sababu you can count that color somewhere else na upate there's a problem, sindio? Yeah. So ukiweka hapa uone it's working well and good. So I think there's no difference hata ukiweka hapa ama hapa. So as far as that is a function that is recognized by what? By this language. So Mr. Kabila. Okay. We can continue. I think you don't have this package. Ama mko nayo? Mr. Kabila, do you have this package? The GGPLOT R.
Yes.
Oh, I think it's
I just loaded it.
Oh yeah. Now you have to understand what is the use of each package. So for example, what is the use of GGPLOT R? What is the use of GGPLOT? GGPLOT R, it will come just to assist the GGPLOT 2 to produce more beautiful plot based on graphs for researcher with the advanced programming backgrounds. So this is just like a supplement to GGPLOT 2. So but now this package comes with some statistical part of it, not only visualization but the theoretical part of statistics. So for example, if you check what is happening here, you will note that what we have is a GGPLOT. Yes. What are we plotting? We are plotting the empty cars, this data set here, and we are plotting the MPG and WT. MPG is here and WT is here. Yes, up to there we are very correct. Plus, what are we doing? We are just plotting this point here and point here. Up to that point we are okay. So but now we want to add something else. We want to add something else here. We want to produce a smooth line, a smooth curve. That's why we are introducing these additions here. I want you to be very keen here because what we are doing ilikuwa inaishia hapo, si ndio? Ilikuwa inaishia hapa up to that part, so that execute hii part, then let's try to call p. Yes, you can see what we have here is just the MPG and WT up to this point. So but now I want to add something else called the geom smooth. So I can add anything that I want from here now using the addition sign. Let me show you. Yes, up to this point I want us to go up to that point. Acha tukoti nyingine, so acha to run mpaka hapo, then we add what are we adding? We are adding a smooth, the smooth part of it. Let's see. Let me remove this part here and execute up to this point. So what I'm telling you is that we have executed this part here plus this part here, then from there we have added what you can see. What we have here is line of the best fit. Producing line of best fit in statistics, I will take you back to the regression analysis. If you haven't done this topic, you will do it later. Or in regression analysis, when you want to produce a line of best fit, or when you want to produce the equation of a line, you will have to use the LM function, to produce equation of the line. But here I wanted to produce a smooth line under this data set. Then from there, this is the statistical correlation. I have used the Pearson's method. A label of x is equals to 20. This is captured at this point here, the x-axis here. So this is just the spacing of point. The spacing of point. For example, if we insert it, what happens? Check. So now inakuwa kidogo. So that is what we call by spacing. And you note that here we have our equation of the line. So this is r. We have not actually the equation. We have r negative 0.87. This is the p-value of that particular line. Yes. From there, let's see now. If we don't want to have jump points, you can have bars. So from the empty cars, you just produce. Let me show you. GGPLOT empty cars as the x ikiwa gas. So remember, in bar plot we only need to have one variable that you want to plot. The bars of x and the bar cars. Then geom, instead of point, now we have the bar. When you run this command, what do you get? You will get bars here. So we have 3 gears, 4 gears, 5 gears. Can just content like that. We have the histogram. The empty cars is that x mpg. Then geom, instead of bars, we have the histogram. So this point here will produce what? Will produce the histogram. Yes, we have the histogram for mpg. Then we have the counts. We can have the ggplot for point of empty cars, and we can color what? We can color this part here. For example, check here. We can color the point. So that is what we mean by coloring the point here. And let's see. If we bring this part here, let's see what will happen. I think imestakabila, unaona it's possible, sindio? So for coloring it can be on this point here, so you can insert it anywhere. So yes, from box plotting you have just to insert, instead of histogram, you insert box plot. Check here, there's Lattice, you remember, but here now you have to understand what each plot considers most. We have our y as mpg, we have the what are we using to form our box plot as our main factor is the cylinder. Yeah, that is what we mean here as factors. And you will note that we have them here. So we have this part here. So I think you can execute these others at your own time. Let's jump direct to what we are supposed to cover today. Today we are supposed to do something that we call the lattice graphics. Lattice graphics is another package that is used for what? That is used for graphics. Is just another package that is used for graphics. Let's see what will happen here. So the lattice package is just a powerful and elegant data visualization package for R programming. It has emphasis on multivariate data. On multivariate data, it is inspired by trellis graphics. So I think you will have to do a lot of research to understand some graphics here. For example, you understand what so that you may understand what you mean by trellis graphics, for example, and many others. So we will be using the dataset series to demonstrate this part. So let's dive into it. This lattice package, it uses XY function. In GGPLOT 2 we were using GGPLOT function. You understand now the difference? But now in lattice package we use the what? We use the XY plot function to create the plot. To create a plot. I expect you to load the package first if you haven't, and everything will be okay. So you just click on tools, install package, then from there you write the name of the package that you want to install. This is the lattice. Lattice package is here. Then you click on install if you haven't installed it. And then it will be installed. From there you call the package. Now you call the package lattice. You call the package Yes, I have called my package. The syntax for this package is very simple. UXY plot. What are we XY plotting? We are trying to XY plot the sepal length and sepal and the petal length, then comma, from which data? From the iris dataset. So this is the normal syntax, and if you want to introduce any other function that is used inside this programming language, you can introduce it anywhere in between. You can introduce it here ama mbele hapa, sawa. So this is the syntax. So this syntax is, let me simplify it. So is xy plot, uxy plot, x y, so not that one, x, then we use this sign here, x y, then comma, then you specify your data, so your data is equals to blah blah blah, so that is it. That's the normal syntax for this language, so I'm sure up to now you can tell if a certain code is in which package. For example, in GGPLOT 2, what were we doing? We started with the data here, then aesthetic part here where we specify what we want to include in our graphics, then geom point or geom function. The function will take any operation that you want to include in your analysis. So when I execute this command, I expect to get an output of petal length here and petal and sepal length. You can see we have and a visual window so you can check on that different in syntax. Okay, let's introduce something else inside our graphics. We have specified now, check on this code here. Remember, this code can be actually in one line, one continuous line, but I've decided to break it down. I have the xy plot, sepal length, and sepal and the petal length. From which data? From the iris dataset. So anything that follows after this part of specifying the data that you want to use must be a function in R. Otherwise, it will not. The compiler will not understand what you want to mean. So for example, when we have then group here, group is equals to species. Group by itself is a function under this package, under this language, I mean. When you want to group something by, you can group either point by species. See that? You can group, actually that is what is happening here. You can see here what we have is point, we have petal length and sepal length. Now point where these two variables are meeting is what you are seeing inside this graphic here, or inside this plot. So but now we can't tell which plot comes from which species. So that's what we want to do here. I have now grouped by species. I want one of you, just a matter of common sense, to tell me what is auto.key. Mr. Kabila, do you have any idea there?
Yeah, but nimerun yangu nikaona auto.key kama key like key of a plot.
Hatukupati. Okay.
Bado unipati?
Okay. Ni kama uko na idea. Auto-key is used to replace. Sawa. Are we together? Auto-key is used to do automatic replacement. For example, you will note that what you have here are different points, but they have the same color. So when I apply group by command here, I want to do automatic replacement of specific point in this graphic. So pahali point iko, it will just be replaced by the new function, for example, we have you can tell which point comes from which species now. So are we together? Yes. So this is automatic replacement of points. Now with the species, we can, I think now you have understood what you mean by the auto key, where auto key is equals to true. I want you to replace, or I want the compiler to replace the specific entries. Any question up to that point? Do you have any question, please? Do you have any question, guys? Mr. Kabila, I think we are together. Joseph, we want to hear from you. We want to hear your voice.
Yeah?
Unaelewa what we are doing?
Yes.
Okay. I think we can continue. So I think we can continue. You can change the values on X and Y labels, and also add the smooth lines. So now you can add a smooth line in this data. And now how do we do it? We can have just our XY plot, petal length, the sepal length, petal length. So from which data? From erased data sets. Up to here, I think we are very okay. But now, from this part here, anything that follows the data set or the data source must be a command. So when I say when you type is equals to C P then comma small. What do we mean? We mean that what this command does is that it takes point from P, this point here, and gives us a smooth line, or the how do we call it in statistics? Line of the best fit. Line of the best fit. When you say xlab is the same as x-axis in this language. So when you want to replace a certain or a specific axis, you can use the xlab or ylab. So xlab is equals to, I want to replace now the petal length, for example, by this part here, the miles in US gallons. The y part here, the circle length, for example, we can replace it with weight, blah blah blah, at this point. So yes. And remember, when you are executing the command, when you insert your cursor here, so this bracket starts from here. See that? It opens from here and closes at that point. So everything is inside the bracket. See that? So when you execute the command, everything changes now. This part changes and this one changes, and we will have line of the best fit. See that? Let's see. Yes, we have line of the best fit. We have line of the best fit. But now you can we can try to maintain. You can try to maintain the colors of the colors for different species. Let's see how we can do it. I quickly know what is happening. Error expected. Is it this one here? Ni bracket gani ya tujaweka hapa? But this line is not continuous. I think up to now you can try to fix it. Just to try to fix. You can try to fix it. So let's continue. You can also create plot in multiple panels based on groups. Based on groups. Remember, we have three. For example, when we do XY plots for different species, for different species, you remember the use of this sign here. For the first, what type of operator is this one? I want to hear from you. When you wanakumbuka our first class, this on Tuesday last week, which type of operator is this one? do the XY plot of sepal length and petal length for all species. For all species, we are grouping our data into species. What is the data? Our data source is the iris, type is smooth, scales is equals to free. When you specify scale to be free, you are telling the compiler to choose any scale that fits to our data. So yes. So when you execute the command, what do you get? You get graphics per what? Per species, group by species. So you group by species. Lattice package. The Lattice package can produce a 3D graphics. 3D graphics using the cloud function. Now, yes.
But hiyo scale equals to 3
Aki Mr. Kabila, your sound inaongea ikikatakata. Hebu ongea sasa.
unanisikia?
Yes.
Umesema hapa na hii argument ya scale is equal to 3. Kama inamaanisha nini?
Mbona?
Scale is equal to 3. Inamaanisha
you are telling the compiler to pick any scale that can, yani ni kama nikwambie, you are free to use any scale that you feel like to use. Sawa.
yes.
Yeah, that is it. Now we can do a 3D scatter plot. This 3D scatter plot, we will be using the cloud function that is inside the Lattice package. So now you up to now I'm sure you understand that a specific package comes with some functions, or there are some packages that comes with their own packages or sub packages inside. So now let's try to create a 3D scatter plot using this type of function that we are calling the cloud. So the syntax is very simple. You specify your two data, the data that will take x, y and z axis from a specific, let me reduce this to here. Yes, mpaka hapo. Actually these are comments, so I expect you mweke easy the ashes you consider this answer to say that inform the compiler that these are just statements. So this is the syntax for cloud function. You must give three variables. So these three variables will take x, y and z axis. When I say z, I'm sure mnaona hiyo z pahali iko the third eye, sindio? Kwa your Cartesian plane z kuna pahali iko. So you give the first one, second one, but now the third one we don't use this sign, we use the multiplication sign. So we use the multiplication sign here, the petal wing, then you specify your data. So the syntax is like this one. So it's cloud, cloud, yes. What are we clouding? We are clouding x, for example t. So then y, which is the other part. The other part is let's say p, then comma, then you specify the data, then you are good to go. So this is the syntax that we are talking about. So hapa kwa data you must specify data is equals to, then you give the name of your data set. So when we execute this command, what happens? Let's see. You can see we have this is y. This is y, for example. Where is which is the starting point? I think it's here. Yes, this is x, this is y, this is z, this is z, because this is our z, our starting point. You can see where the arrow is pointing. The arrow is pointing this direction, the other part this direction, and our last part of z axis is pointing to that part, to that direction. We can use the group argument to color the point. So remember, this point we don't know whether they came from which species. We can apply the group by what? The group by command. The syntax is simple. This is x, y, z axis. So from which data? From the recent data set. Group by species. Auto key is equals to true. Auto keys replace this the new point of species with a specific color. Just a normal replacement. So let's see. Yes, you can see we have replaced them. So we have replaced those parts. Let's try to use another data set that is called the tooth growth data set. It's inbuilt in your R Studios to demonstrate the box plots using Lattice package. So first of all, you have to understand the data first. So you run the command for tooth growth. And under tooth growth, what we have is we have length. This is soup. This is the supplement. Then we have the dosage. Then we have the dosage. I want you to understand. First of all, actually, you have to understand data first before you do any analysis. This is length. I don't know in which the data is in which measure. I don't know whether it's centimeter, millimeter, or then we have the dosage. We want to have box plots using this function here. So the Lattice package will provide you with the box plot function. We call it GGPLOT function that can be used to create a box plot. For example, y is equals to tooth growth $dose. Up to now, I'm very sure you understand what we mean by what does this sign do in this language. We are taking the dosage, this part here, the dose, then what are we taking as our factors for producing the box plots is the dose itself. So now, is the dose itself. Let's see. From the we have the data here, and now we apply this function here to give us the box plot. What we have here is the dose from tooth growth data. So what do we need to write or to display on our X lab is the dose, and Y lab is the length. So then from there we can have box plots. So we can have box plots. Now I want you to research and tell me in your project the use of this len, the use of len here as far as the lattice package is concerned. So the use of len as far as this package is concerned. You can use the panel arguments of box plot function to make a violin plot. Let's see what is a violin plot, because tunaweza kuwa tuna produce some graphics here and unaweza kuwa hujawaisikia. So what is the use of violin plot? Nataka tu mmoja niambie. Use of violin plot. Ladies in the house. Hey, I want to hear from you guys. What is the use of violin plot? Mr. David. Mr. David, what is the use of violin plot? Then from there to enter Conjenga.
No good idea.
Okay, the yes is called. I can see I've raised your hand. Tell us.
To visualize the numeric data.
To visualize the numeric data here, very good trial. But I can use even the pie chart to visualize the numerical data. So I want to get a specific word. Claire, do you have any idea?
No.
Oh wow. Anybody else? Mr. Patrick, do you have any idea what a violin plot is? Okay, let me tell you. A violin plot in statistics is just an extension of box plots, and it is used to visualize the distribution. So it's used to visualize the distribution of numerical data. You remember very well in your mathematical tables. Ukienda kwa the chi-square, for example, the chi-square, the graph of the chi-square, even before you are told you are on chi-square table, you will see the distribution of that graph and know you are in chi-square, sindio? Or ama tuende kwa normal table. In normal table, I expect the graph, for example, to be symmetrical, sindio? To be symmetrical, so that the positive and negative part, they are equal, sindio? That is how we specify, or how you can tell a graph follows a specific distribution. And now violin graphs, they are used to show the distribution of this numerical data. It tells you that this numerical data has this shape, then you can tell which distribution does your data fall into or fall under. So and let's now produce the violin plot. Panel 1, panel dot violin. Tukiingia kwa hizi vitu wale hatutatoka. The panel dot violin. Panel is a command that is used to display graphics and a specific data set. Unapata the specific data set. For example, you can produce a violin and a data set called the iris. So we have to use the panel function. We have to use the panel function. Just to go to somewhere, research on the panel function in Lattice package. So this is the shape of our distribution. This is the shape of our distribution. Dosage of 0.5. What is the shape? It tells us that the first entry starts from 0 up to around 27, but we have so many of length of 10, so our data is concentrated more on 10. So yes, so the other dose one, you can see the data is concentrated more on 15 to 16, 17 there, and inaenda uniform mpaka hapa kwa 25. Then dose 2 is concentrated more on 25, and the minimum value is on approximately 15, and the maximum value at that 6 there. So our data is concentrated more on 2050 value. So yes, so you can tell which figure follows a normal distribution. For example, which dose 1, dose 2, dose 0.5, dose 1 or dose 2, which one among 3 follows a normal distribution, or the distribution is almost normal? So I can say we have this one here. I can also say hii inakaribia kidogo, but inakataa because of this length here. So from 15 to 27 we have nothing, but everything is concentrated on 10. So hii hapana, hii tunaipiga nje. So that's how you learn data. Yes, you can also create multiple plots based on groups. So for example, yes, just run this command here. This is for box plot. Yes, this box plot here for specific what? For specific dosage. a specific dosage. Check the syntax here. What do we have here is box plot of len supplement dose. We have our dose here. The layout part is to display the output of length. Here, for example, when I say 3 2, I want you to tell me the difference on the layout. You can see what is happening. Send up this layout of 3 length 2. Send up you out of 2 2, for example. This is the layout. This is 2 2 layout. We can have 2 3 layout. Let's see. 2 3 layout. Let's have 4. That is 4 3. Now I can have 4 2. Layout of 4 2. Let's see. Layout of 4 1. I think you can tell the best layout that you can have. So and from there you can produce the violin plot per dosage. This is the line plot. This is not line plot actually. This is a dot plot. So this and dot plot. And dot plot will not be in W plot. So this is box plot. But for dot plot you just type dot plot. So yes. So I think the syntax is very simple. Len supplement dose, then from which data to it, layer 31 h lab or lab. Yeah, very simple. What are you not understanding this part here? Remember, this part here is for specifying a specific word, for giving out specific columns or grouping by doses. We can have a strip plot in this Lattice language. So you have to do more research on the use of these graphics. On use of these graphics. So strip plots. What is a strip plot? Nataka kusikia kutoka kwenu. What's a strip plot? I want to hear from you, scholar. Okay. Anyone with an idea? Mr. Bright Barasa. You are very new. to this class. I haven't seen your name appearing in this Go class. What is a strip plot?
Can I try?
Yes.
It plots values
Uh-huh.
along one unique axis.
Along one?
Unique axis.
Very good. Very good. Yes. Another one? Claire, present the engagement. What are strip plots? Claire Wedimo. Claire, we are waiting to hear from you. Mr. Kabila,
Yes,
what do you think?
hapo sina maoni.
Hauna content hapo?
Hapo niko nje.
Okay. Plotting data using generic features. Very good try, Mr. Joseph. David, you can tell us.
This looks like these strips of data that will be along a certain value. Like there was one speaker who said along a certain axis.
Very good.
Yeah.
Okay. Actually, that's the answer. So the data must be in a certain line or a certain axis, a specific axis. So now, strip plots will just summarize what? Will just be used to summarize univariate data sets. So it will be summarizing this univariate data set on a graphical data analysis technique, that is for our case using the Lattice language, and then data must be on horizontal axis or a specific axis, which is the value of the response variable that we want to plot. And the vertical axis on which the values are set, for example, to be 1. So on strip plot, the values must be in one axis. The syntax is very simple when you want to create this strip plot in Lattice package. So strip plot can be created in R using the strip plot function of this Lattice package. Should I tell you what a len is? You just go and do research. Now the strip plot, you just use this function here, strip plot function. So anything that you write inside these braces will be executed. Will be executed. But if you write something wrong inside here, that is not that does not follow the syntax for normal data analysis, for normal programming in R, or rather the syntax that are accepted by R programming language, then your code will be wrong. We are strip plotting docents from which data? From tooth growth. Jita dot data is equals to true. I expect you to tell us what is a jita. What is jita function in Lattice? What do you understand? What do you understand? What is jita? What is jita? Okay, jita here, jita function here, remember this is a function. Jita dot data is equals to true. Jita is a function that is used to return numeric of the same length as the data used in a specific analysis. For example, in our two-thing growth, I want to return the strip plots of data with specific data length on this particular data set. Are we together? Yes. Another thing is the what? PCH. So these things hizi ndizo vitu mnapaswa kukuwa mnajua, zinakuwa kwa your fingertips. PCH, the PCH package, or no, not the package, function is just is used to stand for plot character. So the plot character. So the PCH option in R is used to define the point symbols. The point symbols in function of our plot. So for example, when I say my PCH is equal to 19, it means the compiler will be aggregating all the points from 1 to 19, for example. Then those points are taken to one line. Let's run this code first and see what we are getting. Okay, under those here, when we have dose of 0.5, when we have dose of 0, or just to try to change this one here and see what will happen. Sababu unasema PCH, let's see. Okay, there's something confusing here. PCH and the shape of this part here, they are giving me confusion. What do you think is causing the symbols to change under PCH? Why? I think I can do more research on the same because I know PCH is used specifically for one reason. It's used specifically for one reason. That is for is the PCH is just for plot characters. For plot characters. And what is a character? What is a character? You remember the other day we were talking of point symbols, point symbols, and is character the same as symbols? I think they are the same, isn't it? Yeah. The PCH, you can start from 1 up to any number that you want. So you are just defining the symbols, or you can just do away with them. So then you produce your own strip plots. The other part here, you can produce it direct here, where you are specifying the dose, grouping per dosage. So you have done grouping per dosage. From that point, we can have the density plot. So actually to end a marathon, because we have like 20 minutes to go, and we will call it a day. So I expect you go and go through the concert at your own time. Ukijiuliza, if we remove this and add this, what happens? That's how we will be able to master this language. So we can create a density plot in R using the density plot function of the Lattice package. So this package comes with a lot of functions. Density plot, you can see what we have here. We have the density plot of, but now I want you to check the syntax here. We start with this sign here, the sign of len, then data to growth. What are we plotting? Are we plotting point? I want you to tell me why we have force statement here. Why do we have force statement? Why do we have force statement, guys? Or I want you to insert t, the true, for true, and tell me what is the difference between the two. Guys, what is the difference? And the density plot, I don't need, it's not necessarily important to have the point in your graphics or in your visuals. So you can have just the density plot, the line itself, and you are good to go. That's why we don't need this point. Tukiziweka f, that is force, we do away with them. So you can have a density plot, then you group by doses. So I expect to have the one for dose of 0.5, 1, and 2. So for CS groups is equals to dose, auto t is equals to true. This is for replacement, automatic replacement. Then we have it here. So instead of defending 0.5 here, 1 and 2, we have different lines. For example, here we have line blue, which is for those 0.5. We have it here. We have for 1, which is this color. then we have for those two, this part here, so this part here. That is how we do density plot in Lattice package. From there you can have the histograms under this language. Remember, the syntax is almost the same. You just insert the name of what visual you want to produce. So to create a histogram using the Lattice package, we can use the histogram function. We can use the histogram function. That is histogram len data is equals to tooth growth, then break is equals to 5. What do we mean by break? What do we mean by break, you guys? Break is the bad wind. Hey, umesahau haraka. Break is the bad wind of our drawing. The bad wind of our drawing. Then we have something that we call a legend. A legend of a plot will help to understand which series or groups correspond to each bar. So box or observations based on its type, color, both. They are function, the legend function in R. So tumetoka kwa the Lattice package. Now we want to define something here now inside. For example, we can add key here, the top, right or middle, moku left huku, auto key unasema this color, for example, represent this one. We can add the titles here. Sawa. That is the legend. Is it the legend or legend? The way you understand it. So the sample function to create a plot, we have a plot 1, which is a sequence of numbers 0, that is 0.1, and we want to plot. Let's plot this one first here. So this is a complex plot. For example, this is a complex plot. Let's say, for example, we have that kind of plot here. We can decide to add a title here, and let's see what we have here. Add legend to the plot. Now we want to add a function called legend so that we can define some things here. So we can define let's say the axis, everything, anything we can define. We can define anything using the legend function. Remember, our plot or our visual is called what? The plot one here, the plot one, and under this plot we can have legend. What do we need? On X we can have at the top right. At the top right is where we want what? We want our legend to be. Excuse me. Is where we want our legend to be. We can have legend of J0 and J2. So the LTY Z1C. This is the line type. So this is the legend text that I want to display in my legend. Then we have the colors. These are the colors. Remember, colors in R, you can call color based on the numbers. The numbers or colors are assigned to numbers. We will see. Then LWD. LLWD is used to specify the width of the line that you want to draw. So yes. Now let's see. Oh, not that one. This one here. From this plot here. Yes, that's our plot. From there we can execute this code. Yes, you can see what we have here is a legend. So inside and drawing. From there you can specify where you want this line, for example, to be center, or where this legend, where you want your legend to be. For example, suppose you want to change the color to 5. Let's see what will happen. Color 5, you can see color 5 we have this one, and color 3 is dotted. So let's maintain the original colors because they are the ones that have been used inside our drawing. So yes, these are the colors. So when I produce this visual to anybody, one will understand that this color belongs to J0, and the dotted color here belongs to J2. You can modify your legend. Remember, we have inserted it at the top right. Check this one here. We are trying to modify the insert. Is it insert or inset? That is the distance from the margin of this drawing. I want my legend to be 0.05 away from the margin. So from the margin, and let's see. So the other code is the same as this one, but what we have included here is just an insert. So insert. You can see what we have now. We have removed, or we have pushed this one inwards from the margin. This is what we call insert. So if you increase that distance, it will pop out. It will pop in. More. So it will pop in more. If you need to add a legend, to amber plot, pie chart, or box plot, you can use the fill argument instead of setting lines. So for example, let's see this one here. Bar plot table empty cars from gears. So what am I doing here? I am producing a simple. I'm tabling gears. I'm tabling gears, of the empty car data sets. So this is a simple bar plot of those tables. So from there now you can add a legend. And remember, not necessarily for your legend to be on a top right. It can be at the middle, it can be at the top left, for example. Let's see. This is 3, 4, and 5. Yes. Fill 2.4. This is the color of the squares. Borders in black. Let's see. So I want to handle the legend. You can see I have handled my legend here, and we can have it at top. Excuse me. Top left. Let's see. So now it can be here. Either it can be here. So in the kwanza, the first one. So the second one is this one here. So it can be anywhere. So if you want to have shading lines, you can also hand them. You can also hand them to there.
Excuse me.
Yes.
How would you clear the plot or the legend? Because we are able to add or move put another legend to be to the left. But how do you clear the first one?
Okay. How do we clear the first one? Remember, when you are executing this command, the compiler understands there's nothing in your visual output. So now clearing this part here means you can do away with this one here. Let me see. So you clear this one so that you can have the updated ones. Let's see, for example, I think the best way to clear those legends before you update them is just to produce the original graphics, the original plot before legend was inserted. So that tukikuwa na top left, for example, we can run na tukuwe nayo hapa tu pekee, si ndio? If you want to have it at the top right, you can run the command here so that you have the original plot, then you have it at right, si ndio? Yeah, so we don't want to overwrite our visual, si ndio? Yeah. The other one inakuanga at the bottom or at the top. Let me see. Do we have the top? Yes, we have the top one. So you can have it at the top or at the bottom. Okay, let's see. Let's see whether we have the bottom. Yes, we have the bottom. So you can have it anywhere. You can have it anywhere that you want. You can place it with if you want to have, if your plots have shading lines, you can also add them to the legend. See there, to the legend with the density argument, and modify the angles of the lines with the angle argument of the function. For example, if we plot, this is our normal plot, so I want you to check the difference when we introduce the angles in our graphics. Okay, this is density 30, this is density 30. So my lines here under this plotting is of density 30, but now the angle under which our lines stands is 60, so that if you change it to 90, you will have straight lines. You will have straight lines going. You will have the straight lines. So instead of this one, they will just be at 90 degrees from this line, from the bottom. So from the bottom. If you have let's say 100 degrees, angle of 100, I expect them to be like this way, from left, for example, to right, but at an angle of 100. Yeah, this way. From there you can just add your legend. You can just add your legend. Then from there the legend title, you can insert the title here. And this is the title adjustment. This is the horizontal adjustment of the title. What we mean by horizontal adjustment of the title by 0.5, let me demonstrate using this one so that you may understand. You can see here we have a title. This is a legend title. So look, but now instead of having this title here, you can have you can say these are keys. These are keys that you will follow. So these are your keys, for example. And the adjustment, let me check here. Okay. These are original. That is our title. That is the legend title. So that is the legend title. But now I want you to go through this part here for the adjustment. This is the title. This is the color blue, title color. Title adjustment. Title adjustment is the, how do we call it, the font, not really the font, the size, the size. Because if I insert 0.9, I expect these numbers to be bigger, so not really, to be adjusted from the middle of the legend box. Be adjusted from the middle of the legend box. Let's say, for example, let's try one. So one is just there. Please, very tired condition, don't know. 0.4 I expect to be the middle out of 0.1, then just little adjustments compared to the legend box where you want your ticket to be. See where you want your ticket to be. So I think we can call it a day. What? We can call it a day. So